So now you can just talk and write.
So is it recording now?
Yeah.
Cool. So, just getting into our sort of lecture on series and parallel combinations for these cells, how they actually work, and how we're going to be putting our battery pack together. It's really helpful for the team to understand how these cells go together, and how we're actually getting these kind of crazy numbers out of our battery pack. So, starting off, the cells that we are likely looking at using are the Moly cell P42A. So let's just draw an individual cell here. These are the Moly cell. Oh, sorry, just one L there. P42A. And these cells are pretty standard in their voltage output. They can do 4.2 volts maximum, 3.6 volts nominal, and these are pretty crazy in that they can do 45 amps output per cell. This is the max. And so this 4.2 versus this 3.6 just has to do a little bit with the battery cell discharge rate. So if we look at sort of a graph of voltage versus time, at a fully charged state, at 0 seconds, we're going to be outputting this 4.2 volts. 4.2 volts. As we use it for a little bit, the voltage is going to drop pretty quick and sort of linger. Wow, look at this. Around this. That's really cool, dude. That's actually really accurate.
We're gonna kill this, bro. This is why I came on his team.
And so we're looking at it lingering around this actual 3.6 volt mark. And it'll linger around this 3.6 volt mark for most of its lifespan. And after it gets pretty much drained, it'll start dropping off pretty quickly. So this is why we like lithium-ion cells, is because we can have a pretty stable voltage for a good amount of time. And so this stable voltage here is the 3.6 volts nominal voltage that we're actually looking at using. And so let's just, as an example, let's assume that the battery never really gets this 3.6. We're just going to stick with this 4.2 volt maximum so that we can do some sort of maximum voltage and amperage calculations here. So let's say we have this load, let's call it a motor. We'll just give it a positive and a negative. And let's say that this is, we'll just draw a little circle here to represent our little motor. This is going to be a DC motor, not an AC motor like we're using, but we'll just make things simple. Let's say this motor likes to magically runs at 4.2 volts and requires 45 amps, or can take a maximum of 45 amps to run at peak power. And we want to run this motor at peak power. So what we would do is just introduce one of these battery cells, really, and we'd be able to run this motor at this 4.2 volts and 45 amps. Now, if we wanted to, say for example, have another motor, we'll just draw another little DC motor here, that we want to run at 4.2 volts, and we want to run this one at 90 amps, right? This is a higher power motor or something. It can take more amperage, generate more torque, more power. And so let's see what we would really want to power this with. So if we have one of these cells, we wouldn't have enough to really power it at its max amperage. But what we can do is introduce another cell in what's called parallel configuration, right? So if we represent the amperage coming out of this cell as little lines, right? Let's say we have a couple little lines coming out. And let's say we have another couple little lines coming out of this cell. And we actually join them together here at the top, what's called parallel configuration. Parallel configuration means we just join the positives and negatives together. And now all these little lines are combined, and so all the amperage is combined. The voltage stays the same, right? but the amperage is combined. So now, out of this little parallel combination of two cells, we now have 4.2 volts, because the voltage stays the same. Again, we're assuming that it never really drops below the 4.2 for the purposes of this, but the amperage actually increases to 90 amps. So we're doubling our amperage. Now, if we wanted to run, for example, like our motor can take a maximum of 470 volts, and it can take quite a bit of current. I believe it takes 340 amps maximum current. We would really want to be trying to get close to those numbers, at least on one of those fronts, on the voltage or on the amperage side. But let's say, for example, we want to run, one of the amperages that we're looking at running here for this motor is actually 270 amps. This is kind of an overshoot, but if we're looking at running 270 amps, without looking at the voltage right now, we would need to have a parallel combination of 1, 2, 3, 4, 5, 6 cells in parallel. So that is one little group of cells connected positives with positives and negatives with negatives, right? So this is what we're calling the parallel configuration. Again, positive here and negative here. So this parallel group of cells would output, again, 4.2 volts at 270 amps, which is kind of crazy for just 6 cells. Now, say we wanted to step up this voltage, right? How do we increase the voltage? Well, we would increase the voltage by actually stacking cells in series. So if we take a look at just 2 cells in series, right? If we have one cell here, one cell, we have 4.2 volts and 45 amps. And let's say we got 5 little lines coming out the top. That's 4, 5. And then let's say we stack another one underneath it, and we got another 5 little lines going out the top. And we bridge these together in series, right? So where this is my positive, negative for this cell, we would tie the positive of this cell to the negative of this cell, and then our outputs would be down here and up here. So we still have a positive and negative, just like any cell. But now these cells are combined together. And think of these like a little booster. Let's say the bottom cell boosts from 0 volts up to 4.2 volts, coming up to the top. And let's say the second cell takes in these 4.2 volts and boosts it up another 4.2 volts. Now, since our amount of current flowing into this battery is the same as what it can output, we can't really get more current out of this combination. But what we can do is, again, increase the voltage. So in this combination, we would have 8.4 volts at 45 amps, right? So we can kind of take this concept and run with it. If we take this series concept and combine it with our parallel concept, we can start stepping up the voltage pretty dramatically, even if we just keep the amperage the same. So let's say let's make another little group of cells. We'll just make another 6 cells here. 1, 2. They get more lopsided as I draw them. That's 4, 5, and 6. And we're just going to pretend those are aligned with each other. Again, let's join these in parallel, which again is positives to positives and negatives to negatives. So this combination here is again 4.2 volts at 270 amps. But then when we join these together, if we join, again this is positive and negative, if we join all these together, positives to negatives, sort of like this, now we've created what's known as a battery pack where we have series and parallel configurations. So now even though each of these segments up here is 4.2 volts at 270 amps, what we've created altogether, so let's draw this little bracket here. We've created 8.4 volts max at still 270 amps. Because again, our amperage doesn't increase in series, but our voltage does. And if we start adding these cells together, in our case, to be rules compliant, we have to meet some amperage and energy and weight limitations. So kind of working within those parameters, we decided on a 270 amp, and I believe it's 58.8 volts in series. So that is a 6P 14S configuration, where P is parallel and S is series. So we'd have basically 14 of these segments in line with each other. Right here, just in line with each other. So it would be 14 in series. And we would take each of these segments. So let's draw these segments as kind of like a little box, because that's really what they're going to be. Now the actual arrangement of the cells might vary a little bit, but let's say we have 1, 2, 3, 4, 5, 6, and then we have 1, 2, 3, 4, 5, 6. Let's assume this is like 14, right? Let's assume this is 6 by 14. We would take each of these little segments and string them together inside of an overall battery pack, where we can actually ramp up that voltage to what we need. Now technically, we could just make one of these individual battery packs output the stuff that we need, but per the rules, they need to be separated into segments. And so what we've done is we've strung 8 of these segments in series. Again, each of these segments is 270 amps, 58.8 volts. And what we've done is we've strung them in series to increase the voltage, so that our overall battery pack can output 470 volts at 270 amps. So that's where we're getting the numbers from. And that's kind of how these parallel and series configurations work. That's the reason why each of these segments has to output 270 amps. And that's the reason why each of these segments only outputs 58.8 volts per segment. And that's how we get to these numbers. Eventually we'll cover where we actually pull these numbers from, why we're running these voltages and amperages. Again, this amperage right here is subject to change. This is just kind of a number that we started with to be safe. We will actually go in and calculate out how much amperage we really need at a later point. But this is just so we can start prototyping.